This is the 12th episode in a series about designing and building a clock for my relay computer. Last time I put together a breadboard prototype of a crystal oscillator clock, and that means that along with the relay-based clock, I now have two working prototypes, and so it's time to move on and to designing the final PCB. Before I can do that though, I need to bring all of my designs together into a series of schematics, and that's exactly what I'll do in this episode. So without further ado, let's get going. And to design my schematic, I'll need a proper tool, rather than the drawings I've been doing so far in my slideshows. And my tool of choice, mainly because it's free, is Easy EDA. Now, I've been using this for some time now, and as you can see in the list of projects that are left, I've already got the schematics and PCBs for several of my computer's cards. Eventually, I'll have designs for all of them as I'm going through converting the wire-up cards to PCBs. And all of these designs are shared and made public, so you can get more details on that at my website relaycomputer.co.uk, and if you go to /pages/progress, you can see where I'm at with each card. Anyhow, first job is creating a new project, and I'll name this consistently with my other cards. By default, Easy EDA starts a new project with a single schematic sheet, but you're not limited to one, and you can create as many sheets as makes the design easy to understand. So a good place to start with the design is the connections to the rest of the computer that run along the back of the card. Here's an example from the XYMJ register card, which shows the four connectors on the Y backplane cards. Now, if you're not familiar, here is the four backplanes used in my computer: W, X, Y and Z. Each backplane can hold 5 cards and groups together the connectors that are commonly needed between those groups of 5 cards. Here's the type Y we've just been looking at, and going left to right we have the address bus, control Y bus containing various control lines that Y-type cards will need, the data and ALU control bus, and finally on the right the power connector. The clock card I'm designing now, however, is a type X card, and so the connectors are different. Left to right again we have control X bus, address bus, the data and instruction bus, and finally, again, the power connector at the right. The address bus and data part of the DI bus are exactly the same lines seen on the Y backplane. That is, they're passed through from the Y backplane to the X backplane. Likewise, the instruction part of the DI bus comes in from the other backplanes, and ultimately all of these lines go off to the upper enclosure and off to the various control switches and lights. Right, let's put this side by side with these EDA so we can keep track of our connectors. And whilst I remember, I'll update the sheet description at the bottom right, and this is a good practice and makes it easy to identify what each sheet is for and what it's describing. Right, connector time. Let's start with the power connector, and for this I'm just going to copy and paste it from the register schematic. As you can see, the pins are all in the same order, although here I have 4 pins for 12 volts and 4 for ground. And this is to quadruple the amount of wires the power can travel over. Absolutely overkill for the amount of power this card will consume, but it just makes good use of the pins available. At the bottom here is something that's not shown on the original backplane diagram on the left there, and it's the diagnostic power VD. This will only be powered when the computer is in the stop state and ensures the buttons that drive control lines directly can't be activated while the computer is operating automatically. At the moment there's no card that makes use of it in the lower enclosure, but having it here just leaves things open for future options. Next, let's bring over the DI bus, and for this the nearest match is the DC bus, which has the same pin count and is the same type of connector. Checking the original diagram, I can see that the data bus part is identical between the Y and X backplanes, so the even pins are as needed. So all that needs changing is the name, and then renaming the odd numbered pins as required, and that's the DI bus connector all done. Next up is the address bus connector, And we can just take a direct copy of that, although I will rename its identifier to P2, as it's the second connector counting from the left, followed by P3 and P4, the power connector at the right. Last up then is the Control X bus, which has the same number of pins as the Control Y bus connector, but all the lines will need changing. Now it's crucial to get these pins in the right order, otherwise we'll have tons of cross lines and nothing will work. Now annoyingly, renaming the pins on the right moves the text over. I think this is a new feature that I don't remember happening last time, but if I push the main connector to the back, I can then pull the labels back to where they came from. With those done, I can repeat the left-hand pins, although here there's a different mix of unused and used lines, but no problem as I can just copy the connection ports. So that's our set of connectors, and each of those flag-shaped things will act as a link to anywhere else in the schematic where we use the same name port. This means we can pick lines up on other sheets and reduce any clutter on the schematic as a whole. Now not all of the lines coming into the card will be used of course, but we label them up just for consistency, and then also for my next X-type card I can just copy and paste the entire sheet. Right, that's the connectors done, so let's do a save, and then we can move on. Ooh, actually, just before that, I obviously cheated a bit by copying and pasting those connectors, but if I was genuinely starting from scratch, it'd just be a case of looking up that part like so. The magic here is knowing what to search for, and in this case it's an IDC connector. And they're the through-hole variety rather than the more modern service mount type, or SMD for short. Let's go for the 20-pin variant. And here I've matched 20 items from the system generic class. Now better still though is finding a match in the LCSC class, which is the sister company to EasyEDA, which provides electronic parts. This means we'll get an exact part match, if they carry that item, and we should also get a schematic PCB footprint and sometimes even a 3D model of that part. Refining the search a little bit further to only include items on a 2.54mm pitch, which is 0.1 inches, gets us down to 41 potential matches. Clicking through a couple of these now, I can try and find out what I'm after. And here's a good one, which is the right-angled IDC box header. I can even click on the part to go to the LCSC website, from where I can take a closer look, access the datasheets, or, as LCSC would most prefer, add the part to my cart and get purchasing. Anyhow, with the part found, I can then place a schematic symbol, and we're back to where I was before with my connectors. Before we go further, I'll quickly create some more sheets and have a bit of a reorganise. Each of these sheets are stored as a separate file in EasyEDA, but when viewing a sheet in a project, you can quickly flick between them with the buttons at the bottom left. Likewise, you can reorder them by bringing the sheet forward or backward. Now I'll update the schematic details, firstly for the crystal clock, then for the relay-based clock, and that leaves a third sheet for the connectors. Looking at the files under the clock project, you can see the 3 schematic sheet files. Cool, let's get on then and place some relays. Again, I've already got a ready-made relay schematic from the register design, so I'll nick off with that and place it into my relay clock schematic. This will bring along with it the correct PCB footprint, and I've even got it linked to the actual part at LCSC. I can also view the PCB footprint and ensure the pins on the schematic correspond to the correct pads on the PCB footprint. Alongside each relay, I'll need the reversed bias diode and a connection to ground, which I can also lift and shift from the register design. After a quick rename of the diode reference, all I need to do now is connect it to the relay coil like so. Once you've laid out wires, you can drag them around like this. So there's always opportunity to have a tidy up afterwards, and we can initially just concentrate on what connects to what. I can now copy and paste the combined relay, diode and ground once, twice, and 3 times, given the 4 relays needed for the basic ring counter. Notice how each paste updated the relay and diode references, so we now have K1 to 4 and D1 to 4. Pretty neat, yeah? Let's give it a save and then I can move on to wiring out the ring counter. To help with this, I'll import a screenshot from my previous video showing what needs wiring to what. This will just save flicking back and forth between screens. First, let's lay down the power supply inputs. Again, I'll nick this from the register schematic, and I can place the 4 of them like so. I can now put a net port down for the stage outputs and rename them A, B, C and D. These net ports are exactly the same as what you saw on the connections earlier, and if I give any of them the same name, then they'll inherently have a connection between them which will get wired out on the PCB. Here I'm prefixing the port names with RC to distinguish them as specifically relating to the relay clock rather than the crystal clock. Let's have a quick tidy. And it's on to the wiring itself. All I've got to do here is replicate what's in the image above, although it's slightly tricky here of course as the relays have their contacts in slightly different positions between the two diagrams. Notice too that we need to keep an eye out for the dot appearing where we intentionally want lines connected. If there's no dot, then it means the wire is crossing over the other one but not connected. This is where misconnections can happen, so worth keeping an eye out and of course check, check and checking again once the first draft of the schematic is complete. There we go, and by the magic of editing I can skip forward a bit to here where I've had a bit of a tidy up and flip the relay stage outputs to the right hand side where it, well, just looks better. When designing these schematics there's a certain amount of artistry involved and it'll tend to lean towards whatever the author finds aesthetically pleasing. Anyhow, let's carry on and hook up the crossover between relay C and D, effectively making an exclusive OR between those stages. That is, we get a high clock signal when relay C or D are active and a low clock signal when both C and D are off or both C and D are on. Next up, let's make a bit of room at the top of the schematic and pop in another relay for the freeze line. But in a change to the original diagram, I'll feed this relay from the incoming freeze line and then connect both common contacts to power and then the normally open contacts to the coils of relay A and C. Oh, actually, that's not quite right. It should be feeding through the C and A outputs like this. This would mean that stage A locks on if the freeze line is set and we're in state A, or alternatively if we're in stage C and the freeze line is set. In other words, if we're in stage B or D, it will run through to the next stage regardless of the freeze line state. This optimisation was spotted by Carl Anderson, who posted in the comments of episode 8. So thank you, Carl. Next job is wiring the clock output, and again I'll prefix this with RC to differentiate it from the output coming from the crystal clock. This comes off the D stage relay following the XOR crossover. One thing I will do though here is pop in a diode to make sure nothing can backfeed into this circuit. It's unlikely there'd be a problem, but obviously if the clock line was held high whilst activating the freeze line, it could hold relay C on at a time where that normally wouldn't be possible. Right, we can get rid of the original diagram image now as we've got the basics of the relay ring counter. I'll just add a title at the top left for this sheet and label up the broad sections of the schematic, and we're looking good. Let's zoom out a level design wise next, and I've pasted in another screenshot showing how the ring counter connects into the overall clock design. Firstly, I'll pop in some LEDs for each of the ring's counter stages, and these will be placed at the front of the card and connect to the A, B, C and D outputs respectively, coming out from the first schematic sheet. I'll just space those out slightly, and then I just need to ground off the cathodes of those LEDs. Next, I'll add some LEDs for when the output of the clock line is high, and I'm using two LEDs here just to add extra visual emphasis on the outgoing clock signal. This needs to be connected to the RC clock line from sheet 1 and will later on be joined by the clock line coming in from the crystal clock. The outgoing clock line needs to go off to the carb backplane connectors, of course, and that can be done like so, which will pass through to the CLK line on sheet 4. Speaking of connections, EasyEDA keeps a list of what lines are present in the schematic, and it can tell you if there's anything that's not connected. Here we expect things like the address, data and instruction bus lines to be unconnected, but everything else should go somewhere, and we can double check that here. Here I've combined the RC clock and clock lines via the wires drawn out at the two LEDs. Clicking on it shows which connection in the schematics are involved. Right, what's next? Well, looking at the diagram I can see that I want some control over when the power is provided to the relay clock. This is so I can switch between this and the crystal clock. This is easily changed by renaming the V inputs to RCV. To control that power line, let's make some room on the UI sheet and go hunting for the switch I showed at the end of my last video. I'll type in the manufacturer's part code and see what comes up. Looks like there's no LCSC matches, but there are 3 user-contributed matches. Again, in terms of the schematic itself, it's largely a matter of style, but the PCB footprint needs to be right, although I could tweak it later if there was a problem. I'm going to go for this one, so let's get it placed. I'll ground the shield around the switch. This also anchors the switch on the PCB and helps relieve the strain when the switch is operated. Now I want to position these switches in such a way that they're up when on, or when viewing the PCB direct on, with a switch to the right. Looking at the footprint manager, I can see which pins relate to where on the footprint, and in this case pin 3 will be connected in that case. So let's bring in the power on pin 2. And here's where you have to be careful, as that's not actually connected, as the switch is slightly offset. Right, there we go. And let's rename that back to V, as that's the main power supply coming in that I need. Then I'll have another switch, exactly same make and model, and I'll ground that out, and looks like the other ground isn't connected. Right, let's get that sorted, and this is the risk sometimes with user contributed items, but easily fixed. Right, where was I? So bring pin 3 from the first switch over to the common of the second switch, and then I can take pin 3 of that switch over to the power supply for the relay clock via RCV. And the other side of that switch will, of course, end up powering the crystal oscillator clock. Last bit for the relay-based clock is the Halt Latch, so I'll quickly get that in and set up the power inputs. The Halt line comes in on the left into the relay contact, but also needs to feed back into the relay coil. Now looking at the diagram here, though, I need a way of interrupting that feedback line via one of the front panel switches. Now that comes in via 2 lines on the backplane connector, and to differentiate them, I'll need to rename them slightly. This is needed so they come through as separate tracks when laying out the PCB. I can now add them to the first schematic sheet and hook them up like so. Finally, I can hook up the RC freeze line like so. Now actually, that's not the only way to operate the freeze line, and we need to handle the FRZ line, which is active when the run-stop switch is in the stop state. This also gets a diode popped in to make sure we can't backfeed the FRZ line from the latch relay here. Cool. Actually, I'm going to move that latch circuit to the UI sheet, as it will be shared between the relay and crystal clocks. Good. Okay, that's the relay clock done, and that's where I'm going to leave it for this episode. Next time I'll finish off the schematic and lay out the crystal oscillator clock. But for now, thanks for watching, and I'll see you next time.